right. So within the crust of the Earth, of course, we have these different. This is just for the crust. This is the percentages of the different atoms that we find in the Earth's crust. And what we find, and so this is true for for the Earth, the entire Earth, is there are these crystalline structures that form when the molten Earth cools, right? And it cools in various ways. We'll talk about that a little bit. And that is when it cools and it causes an orderly structure. That is what we call minerals. Right. So all right. So the minerals have to have these several conditions for something to be considered a mineral. It has to be naturally occurring. So you know, for example, here's something that's not a mineral. Like, you know, you probably heard of like cubic zirconium, right? That's something that's manufactured. If you manufacture it, it would not be considered a mineral. It has to be a crystalline. So it forms crystals, right? These crystalline solids. These are things that on the molecular level, you get this. You get the same atoms or the same arrangement of atoms repeating. Oh, well, that's pretty much what the next thing says. They repeat over and over and over again in a nice orderly way. Like for example, if you ever take a look at a table salt, table salt is a wonderful little cube. If you look at it through a magnifying glass, and if you break up the table salt, you get more cubes. Or you know, they're not perfect cubes, but you know, they're not. They form that way. They crystallize in a cubic form because of the atoms that make them up. All right, and there's other ones that, in fact, the silicates that I mentioned before, the silicon and oxygen, form a tetrahedral solid, right? So a crystalline solid that's in the form of a tetrahedron. All right. So anyhow, that's one of the. Another condition is they have to have a specific chemical composition, and they can have slight variations, as we're going to see, like the difference between quartz and a ruby, for example. We'll get into that in just a bit, and they have to be inorganic, right? They have to be inorganic. So there's a couple of things. Before we get into that, there's a couple of things that are not minerals. For example, there's a thing that forms called obsidian. It's a type of volcanic glass, for example, that will form, you know, around volcanoes or near volcanoes, and it's black. It's very, very dark. But that actually is technically not considered a mineral, because you don't have it's not it's not an orderly crystalline structure. It's kind of what we would consider amorphous. Glass doesn't have an overall crystal shape. And so that technically would not be considered a mineral. Let's see. So what else? Gold is considered a mineral, even though it's made of the exact same atoms. But they crystallize in a very orderly way. Let's see. So I mentioned cubic zirconium would not be considered. Here's another one that sometimes people think of as a mineral, but it's not, would be sugar, right? So um, sugar is organic, right? It's made of carbon. Usually, if anything has carbon in it, um, well, a mixture of carbon, oxygen, and hydrogen, then it would be considered organic. Okay, so sugar is just composed of hydrogen, carbon, and oxygen, and so it is not it's organic. It's not inorganic. Okay, so that would even though it kind of looks like what we would think of as a mineral. I mean, it does have kind of a crystalline structure, but it's not. It's made from organic stuff. But there are organic things that will form minerals. For example, like you think about certain sea life forming shells, right? Those shells are usually made of calcium. Um, Anyhow, there you can have living things that form, like uh, well, bones and stuff like that, using calcium to form bones and things. All right, so anyhow, let's move on to the next one. So minerals are classified by the chemical composition. The Each mineral type has the same basic chemical composition, but there can be little variations. That's fine. Um, and of course, it has to have a crystalline structure. Each mineral has the same geometric arrangement, like cube after cube after cube, or different shapes, tetrahedral. There's one that's like a rhombus or rhombohedral. It's called. The hedral part just means that it's three-dimensional. These are always in three dimensions. So remember, these things form from the molten earth, the very very hot earth, and become a solid. And when they sometimes when they become a solid, they form a crystalline structure, and that's one of the main conditions for something to be a mineral. Physical properties, as an expression of chemical composition and internal structure. Okay, so crystals will form. Their internal structure will determine the hardness, the way that they when you some of them there's like weak bonds. It actually has to do with the bonds between different levels or different layers, I should say. And so some of the minerals can, like mica, for example. Mica is a really good example of this. You can just peel mica, like little layers of mica off of that mineral, and that is said to have cleavage. Okay, so what that means, the cleavage just means that there's some bonds that are weak, and those bonds break in the same geometric way. Like you when you look at something, a mineral, I should say, not something, but a mineral, and if it has cleavage, it always has relatively flat. We'll do more of this in the lab. It's one of these things that you kind of have to see. I mean, we'll see pictures. I wish they had some picture. Hold on, let me see if I can find a picture. So this is actually from a picture from your textbook. I just wanted to show you. This is just common table salt. Also, the when we call it as when we talk about it as a mineral, it's called halite. All right, so and you can see the cubes, right? You can see these cubes right here. All right, I will get to fracturing and cleavage in just a second. I just wanted to show you some other minerals. You can see these right here. So you know it's always good to. This is amethyst. If you ever go like into a gem store, you see this. It's basically this purple quartz. This B here is called fool's gold pyrite. All right, so and C here is rosite. You can see that. You can see the color of it. Although the color doesn't, as we're going to find out, is not a really good indicator. This one's hard to say. D here is rhodochrosite. Let's see. E is hermite. All right, so there's E right there. It's that's another mineral. And in F there, this is actually a mineral as well. Asbestos, right? Asbestos. All right. So anyhow, those are some nice pictures of minerals. All right. So here's this is of course SiO2 silica. This is actually just kind of a representation of an artist's representation of the tetrahedral structure that these silicates form. All right, I wanted to show you that. I'm still looking for fracture. All right, I thought I could find a better picture of this for cleavage, but we'll see this better in the lab. But when something breaks, it'll, as it says here, it'll break along the weaker bond, where the weaker bonds are. Okay, that's the idea of cleavage. If a mineral does not cleave, then it undergoes what's called fracture. Here, let's take a look at that. So this is an example. So quartz, for example, does not have good cleavage, right? It doesn't break along weak bonds because all the bonds are basically the same. So when quartz breaks, so just look at this picture right here. It'll develop these bizarre not bizarre. It's just kind of this kind of curved structure, and it's actually called conchoidal fracture. So fracture is kind of the opposite of cleavage. Cleavage is when you have parts of the mineral that will break off, but it breaks off in a very, very nice geometric way. This is not repeating, right? The conchoidal is not. You could break it and that conchoidal part will look completely different if you break another piece of quartz. All right, so that's the distinction between they're kind of two extremes. Cleavage, you have weak bonds in a certain direction, and so it'll break in that direction, right? With fracture, there's the bonds are pretty much the same in all three dimensions, and so when it breaks, it'll break in kind of a there'll be some randomness to the way it breaks, whereas cleavage, it always breaks in the same way, in the exact same way. All right, so they're both examples of breaking breaking the mineral. All right, so here, let's go back to this. All right, and here we go. All right, and so another thing is what's called hardness, and we use what's called the Mohs scale of hardness, and I'm going to show you that. The one thing is we don't use color for a way to distinguishing minerals. It doesn't work very